Okay, welcome back to AC for Electronics ET132B. I'm Art Eggers. This semester, what we're going to be covering is your introduction to alternating current and voltage. Although we call it AC and alternating voltage, we're going to find out have a relationship, a sinusoidal relationship between them. Unlike DC, which is a steady current and a steady voltage that does not change with time unless you change the value of the of your source. In this course, the source itself is alternating peaks and lows at a set rate and normally very periodic. So what we're going to look at in this first chapter, chapter 11, is the introduction of alternating current and voltage. Hopefully in your ET131 course, your DC course, you got an introduction to this at the end. For those of you that took the math course 111, you got an introduction to this as well. I do have a series of videos on here for my 111 course on YouTube. I suggest if you need a review that you go back and look at some of my videos, and if you still have your textbook and some of your material, review that material, because we're going to be relying very heavily on what you learned in ET111, the math course for electronics. Regardless of what other math course you have, if you've taken 111, that's the course to rely on for your background for this course, or your preparation and your foundation. So in this course, you can see in the chapter 11 flash plate here from the textbook, we're going to look at several sections in that book. The last section, 1110, the oscilloscope, we're not going to spend a lot of time on because you're going to be using your information for the oscilloscope in your lab, and you're going to be learning in your lab assignments the operation of an oscilloscope. So sinusoidal waveforms through angular measurement, analysis of AC circuits, and the sources that are normally used for producing alternating current and voltage. So in the first four sections here, we're going to look at those specifically. I'm going to try to keep these videos short so that you're not being overwhelmed and overburdened by a bunch of lengthy videos. I want something here that's going to augment and supplement your textbook and help to identify those areas that may need a little further clarification than what the textbook provides. So in those sections, we're going to look at identifying the sinusoidal waveform and its characteristics, determine the sources, various current and voltage values in a sine wave, describing the angular relationships, do a mathematical analysis of the sinusoidal waveform, and then we're going to get to the introduction of the phasor. Again, hopefully you had the phasor or vector relationships in your ET111 course. A lot of new terms that you have to become familiar with. What I suggest you do is take a look at this slide and get your notebook out and write down all of these terms and identify what these terms mean in your notebook. Keep your notebook handy for new terms and working out problems that you're going to see over and over again. The best way to learn information is by writing it by hand, not relying on a computer and typing in. There's a lot to be said about your hand movements and writing and information that gets stored in your brain. So the sinusoidal waveform, or the sine wave, is the fundamental type of alternating current and alternating voltage that we're going to be looking at in this section, and in this class primarily. You're going to see we're going to fully develop it by the time we get to the end, because we have to understand how a sinusoidal waveform voltage and current is handled by not only resistors, which you've already seen, but capacitors and inductors, which are energy storage devices. We're going to need to find out how do we handle those. And we're going to find out that we're going to handle them vectorially by using a phasor or phasor representation. So in here we're going to look at the fundamental parts of the waveform to determine its period, its frequency, and relate the period and frequency together and learn how to convert from one to the other and flip back and forth. And then in the end we're going to look at some sources or electronic generators that generate AC current and voltage. So the sinusoidal waveform you can see depicted here in figure 11.2 is in one cycle here. We can see that we have a positive maximum and a negative maximum. Those points you need to keep in mind as we get to the phasor relationship become the maximum length or the maximum amplitude for your phasor relationship. If we draw a line straight from that maximum point straight down, or from the maximum point here straight up, the length of that line is going to relate to a voltage or a current, and that will determine, using a vector relationship, whether or not we have a full sine or cosine relationship. We can see here then the polarities of the sine waves and the period of the sine waves. The polarity of the sine wave, the shaded top portion here, then becomes the positive alternation. The negative portion, shaded, becomes the negative alternation. And you can see by the schematic diagram to the right of each of those that that is a direct relationship to the direction that the current is flowing. In this case, looking at the current through a resistor or across a resistor. In this case, for a voltage, it's across the resistor, what the maximum voltage is going to look like, positive or negative. So the next thing we have to look at and understand is if we have a multitude then of these sine waves from zero back to zero again, or one complete alternation, as you can see on the right here in the figure, we identify that as the period of the sine wave. The period is identified from 0 to 0, and then it recurs over and over and over again until you turn off the switch. So the time required for a sine wave to complete one full cycle is called the period, and this will become important later as we do measurements of AC and alternating voltage forms. So let's take a look at a couple of simple examples here. In this one, they want us to determine the period of the sine wave. So you can see we've got 1, 2, 3 complete alternations here that go from 0 in time. Notice that the x-axis here now is identified as a time in brackets here in seconds, and on the up down or the vertical axis here, that is our voltage, and that will be measured in volts. So we have 0 to 4, one complete alternation, 4 to 8, another complete alternation, 8 to 12. So in this particular illustration here, as shown, the time that it takes for one complete alternation is 4 seconds. So that is the period of this waveform. Although it occurs over and over again, the fundamental waveform identifies the period. On these, what I suggest you do is go back and continue this and work the related problems. In this case, they're asking what happens after 5 cycles in 12 seconds. Example 2, show 3 possible ways to measure the period of the waveform. Okay, so how many cycles are shown? So if we take a look at this in figure 11.6, we have 0 to 1 second, 1 to 2 seconds. So each alternation takes a full second to complete its cycle. So in the solution, method 1 says the period can be measured from one zero crossing to the corresponding zero crossing in the next cycle. The slope must be the same at the corresponding zero crossing. So our slope, when we get to the point of measuring the slope here, we can see we have the slope that basically goes right there, and then here we have that same slope. If we could expand that line tangent through the 1 second, that would be our slope. Method 2 says the period can be measured from the positive peak of one cycle to the positive peak of the next cycle. So there's the positive peak of the first cycle, the positive peak of the second cycle. The third method says that the period can be measured from the negative peak to the next corresponding negative peak. So you have three methods here of measuring the period of the waveforms that you see here. Okay, so we can see on the diagram on the bottom, these measurements are indicated where two cycles of the sine wave are shown. Keep in mind that you obtain the same value for the period no matter which corresponding points of the waveform you use. So from 0 to 0, from positive peak to positive peak, from negative peak to negative peak. In each case, they all remain the same. It's the same measurement. So the next thing that we need to look at is another function or another characteristic of a sine wave. That is the frequency. You'll be using a lot of frequency measurement throughout this course. So the frequency is defined as the number of cycles that a sine wave completes in 1 second. So we need to now look at a count of how many cycles in 1 second that occur. You notice, recall that your house current is 60 hertz. That's 60 cycles per second. So in your house current, instead of there being 2 cycles here, there's 60 of those alternations occurring in a 1 second period. The more cycles completed in 1 second is a relationship that equates to a higher frequency. We have a higher frequency. So now you see on this side, we've got 2 alternations in 1 second, or 2 cycles per second. In the next illustration, we have 1, 2, 3, 4 cycles per second. So that's 4 hertz. The other one is 2 hertz. So 1 hertz is equivalent to 1 cycle per second. 60 hertz is 60 cycles per second. Okay, so now that we have the frequency relationship of a sine wave, let's look at its inverse relationship. The inverse relationship between frequency and period is shown mathematically as frequency is equal to 1 over t, which is 1 over the period, or the inverse, the period, is equal to 1 over frequency. So you may have to use your calculator to calculate some of these as we progress through the course. But again, in your notebook, pull your notebook out right now and write down frequency equals 1 over time. Time is equal to 1 over frequency. This is a reciprocal relationship between the two. Knowing one, you can calculate the other with the x to the minus 1 or 1 over x key. What we recommend for this course is the Casio FX115ES Plus, and if you look on your calculator, it may be kind of hard to see here, but there's a button on here called x to the minus 1. I don't recall if this one has a 1 over x because that would be redundant, but you could just do an inverse on that. So using this calculator, x to the minus 1 is how you do your inverse relationship. So if you don't have the Casio FX115ES Plus, get one. They're really cheap. I got this one at Staples and it wasn't expensive at all. Okay, so now we've got our relationships, our reciprocal relationships between time and frequency. Let's look at a quick example here before we cut this video short. Which sine wave has a higher frequency? Determine the frequency and the period for both waveforms. So you can kind of look at this real quick and eyeball it, and you can see that there are more cycles happening on the right than there are on the left. But let's go ahead and count the alternations. 1, 2, 3 cycles per second. Notice it's indicated at the bottom here, 1 cycle, or 1, 2, 3, 4, 5 alternations in a second. So the higher frequency is the one on the right. So the sine wave on the right has a higher frequency because it completes more cycles in 1 second than does the sine wave on the left. So the 3 cycles are completed in 1 second. Therefore, the frequency is equal to 3 cycles per second or 3 hertz. So this is a per second relationship. 1 cycle takes 0.333 or 1/3 of a second. So its period is 333 milliseconds. If you're not up and you're not comfortable with your metric terms, your metric notation, you need to go back and become familiar. Pull that notebook out, make a familiarization for yourself. The difference between microseconds, milliseconds, nanoseconds, these are all important. They're going to become really important then when we start using them again for the values of our components. On the other side, 5 hertz or 5 cycles per second gives us a relationship of 1/5 second for its period, or 200 milliseconds. Example 11.4, the period of a certain sine wave is 10 milliseconds. What is its frequency? Okay, pull out your calculator, type in 10 milliseconds, 10 to the minus third, right? Do the inverse, x to the minus 1, you get 100 hertz. Example 11.5, the frequency of a sine wave is 60 hertz. What's the period? Again, we do the inverse, type in 60. Since it's a per second relationship, that's over 1. So 60 inverted is 16.7 milliseconds, or 16.7 times 10 to the minus third. Okay, as I said, we're just going to briefly introduce what a source is for dealing with AC and alternating voltage. You're going to use these extensively in your lab, electronic voltage, signal voltage and current generators. So you'll need to, and you will become very well versed on cranking out AC sine waves and AC voltages and currents. So in this class, for the lecture, that's about all we're going to identify here. So in the next section, we're going to look at the sinusoidal voltage and current values and some of the ways to calculate them.